In this problem, we're asked to find Kc for the reaction of H2 plus I2 in equilibrium with 2HI. Everything here is in the gas phase. So that means that everything will go into our equilibrium constant K. So K is equal to HI squared. Again, from the stoichiometry, square that, divided by H2 times I2. Those all have stoichiometric coefficients of 1. So this is our equilibrium constant expression. We are given initial concentrations of H2, 1.000 times 10 to the minus 3 molar, and an initial concentration of I2, and that's 2.000 times 10 to the minus 3 molar at this temperature. And then the problem tells us that at equilibrium, the concentration of HI is equal to 1.87 times 10 to the minus 3 molar. So we've got a lot of information here. We do need to set up an ice table. So let's rewrite our reaction, H2 in the gas phase plus I2 in the gas phase in equilibrium with 2HI in the gas phase. So we'll have our initial concentrations, our change, and our equilibrium concentrations. We do not have any HI at equilibrium, so we're just going to put a line through there. And our initial concentrations of H2 and I2 were given, so I'm going to put these in here. Again, in your ice tables, make sure you're using concentration, not moles. Okay, so we only have reactants present initially, and so we know that we are going to form products. The reaction will proceed in the forward direction. So we know that in terms of the change, we're going to have minus some value x, leaving for the H2, minus x for I2, and plus 2x for HI. And again, we're dropping down our stoichiometric coefficient here, so that has to match up. So there's really a 1 in front of these x's with H2 and I2. So then at equilibrium, we're going to have 1.000 times 10 to the minus 3 minus x for H2, 2.000 times 10 to the minus 3 minus x for I2, and 2x for HI. So our goal is to calculate Kc, but right now we have everything in terms of x. We were given one other additional piece of information, and that is that the concentration of HI at equilibrium is equal to 1.87 times 10 to the minus 3 molar. We know from our ice table that the concentration of HI is equal to 2x. So we can set this value, 1.87 times 10 to the minus 3, equal to 2x. Now we solve for x. We get x is equal to 9.35 times 10 to the minus 4 molar. And we can solve for the concentration of H2 and I2. So we already have our concentration of HI. So the concentration of H2 is 1 times 10 to the minus 3 minus x, 1 times 10 to the minus 3 minus 9.35 times 10 to the minus 4, which is equal to 6.500 times 10 to the minus 5 molar. And then for I2, our concentration is 2 times 10 to the minus 3 minus x. And so we'll end up with 1.065 times 10 to the minus 3 molar for our concentration of I2. Now we can take our equilibrium concentrations and plug them into Kc. So remember, our Kc is equal to the concentration of Hi squared, that's our product, divided by H2 times I2. So our concentration of Hi, 1.87 times 10 to the minus 3. We're going to square that. For H2, we have 6.500 times 10 to the minus 5. And then for I2, we have 1.065 times 10 to the minus 3. All right, when we do our math here, we should end up with a K sub C value of 50.6.